Mr. Burke. I'm here to reassess Standard 5.1 that I can apply the derivative form of the momentum principle to solve statics and dynamics problem. The problem I chose was a statics problem. The first thing I did, also the last time I got it wrong was my Chapter 5 test. So I looked back on that and here it is. Anyway, so given my scenario, I first defined my system and I drew my free body diagrams. So looking at this, the Earth is actually wrong. The only thing in my first system is the mass, so you can just pretend that's crossed out. And I had a momentum of 0, so my dp over dt was equal to 0. And I knew that because my momentum was constant because the mass was experiencing uniform motion, i.e. it was stationary. So I knew that I only had two forces acting on the mass, one of which was Ft of the YOC and one of which was Fg. And I knew that they had to equal each other because they were in the magnitudes had to equal each other because they were in opposite directions in only one component of motion. So I was able to say that the tension of YOC was equal to the opposite of the magnitude of the gravitational force, which gave me an easy answer for the tension force in C. Oh, because the question was to calculate the tension in all three wires. Next, after I did that, I wrote the forces FTA and FTB and FTC as products of their unit vectors and their magnitudes, because a vector is equal to the magnitude times the unit vector. So vector FTC became magnitude of FTC times the vector 0, -1, 0. The vector FTB became the magnitude of FTB times cosine 40, sine 40, 0. And vector FTA became the magnitude of FTA times cosine 120, sine 120, 0. And I also wrote a note to myself, be careful here, because at first when I did this, I did sine 60, and I realized that wasn't going to work, because actually I wanted to find the cosine of 120, because this is a 60-degree angle would be on this side. Next up, what I did was that I knew my because my mass was experiencing uniform motion, that the momentum had to be i.e. dPdt had to be equal to 0, and that meant that each component of the momentum also had to be equal to 0. So I knew that dpx. So I set all of the components. So dpx of ftc. The dpx over dt of ftb, etc., etc. I set them equal to 0, and then I isolated ftb to give myself ftb in terms of fta. So I did it. So after separating the component form and isolating, I came up with these two equations. The next thing I did was I simply substituted my isolated ftb into my equation I got from my component breakdown of the y components. After that, I did some algebraic manipulation. I got that the tension force of A was equal to 5,260.95 newtons, and the tension force of B was equal to 6,422.43 newtons. And looking at these seemed pretty accurate on just giving it an eye, because they were on the same order as the tension force in C. Next, I was asked to find the strain in each of the wires. So what I did was I remembered the equation for Young's formula, Young's modulus, which was y equals stress over strain, and strain is delta L over L. So I knew that my strain would have to be equal to my stress, i.e. my tension force over my area, over y. So I simply did that for each of my three wires. Substituting what I knew, and I had to be very careful here because, again, 0.001 squared isn't 0.001. It's actually quite a lot smaller. So the first time I did this, I got it incorrect, hence the erasure marks. But the second time I did it, I did get it correct. Anyway, that's how I solved Chapter 5, Problem 11. Thank you for listening.